In this video, we will try to make a geometric product table, and we will focus in the case in 2-dimension and 3-dimension. And once you see how I derive the table in 2-dimension and 3-dimension, you should not have problem to derive the table in higher dimension. So in 2D, we have a scalar. In geometry algebra 2D, we have a scalar, we have a vector, we also have a bivector, and we want to express all of linear combination of a vector and bivector into a orthonormal basis. So if we can derive the geometric product table for the orthonormal basis, we can it will make our calculation later on much easier by just following the table. So let us first look at the row here means the geometric product from left side, and the column here mean to the right side. So E1, E2 mean a geometric product E1, E2. Yeah, and which is this mean geometric product E1, 2. So let us first focus about 1, 1. That's no surprise from our definition. The definition in the previous video, we get 1. And also geometric product from scalar 1 to vector 1 is E1 because the scalar property, and E2. And also 1 to the bivector E1, 2. Oh, I should make a small arrow on the top for all the vector. Yeah, here, and it's still E1, 2. And this will be the same here, and geometric product from E1 to the scalar 1 is just E1, and that is not hard. The same story here. And geometric product E1, E1, we use the scalar square property. Then because they're orthogonal, they're orthonormal basis, so it's 1. And geometric product, now we are focusing on this one, geometric product from E1 to E2. We choose, now is E1, 2. And geometric product E1 to bivector E1, 2. So that is this one, E1, 2 is equal to E1, E1, E2. So this become 1, and E2, E2. So it will just become E2. And geometric product from E2 to E1. So it will be the E1, 2. E2, 1. But since we would like to express we would like to using the same basis instead for say writing this like E2, 1 and this like E1, 2. We would like everything in E1, 2 because we have derived from previous video E1, 2 is just equal to minus E2, 1. So E2, 1 is equal to minus E1, 2. So instead for writing E2, 1, we write minus E1, 2. And then geometric product to E2, E2 is equal to 1. And E2, E1, 2. Let's write E2, E1, 2 is equal to E2, E1, E2, and we swap the order, minus E2, E1 is equal to minus E1. Then here is equal to minus E1. The same story. We have only one. The last row, we have only one last row to work on. E12, E1, so it's just E12, E1, just E1, E2, E1, just minus E2, minus E2. And this E12, E2, then will just become E1. And E12, E12, so it will be E. It will be E12, E12 equal to E1, E2, and E1, E2. And if we switch the order in this parenthesis, we get minus E1, E1, E2, E2. Then we get minus E1, E1, E2, E2. Then we get minus 1. So we get minus 1 here. And this will be our geometric table that we'll refer to in 2D. Now we will try to derive the geometric product table in 3D, in the case of 3D. Be aware that in this time we will have something, one more object is called the trivector. So in 3D we have scalar, like in 2D, and also have a vector. Also in the case 2D, we have a bivector. But this time, okay, maybe I should say yes. Bivectors, this time we don't have a one bivector like E12, we have E12, E13, and E23. And we also have a trivector, which we are not going to use, but we are not going to use a lot, but it would be nice we just mention it here. So let us first derive for the case of the geometric product from 1 to 1 is a scalar, and to all these different objects is it is just basically copy and paste E1, E2, E3, E12, E13, E23, E123, and the same here, that the different object, two geometric product from different object to scalar number 1 is just copy, yeah, which nothing changes. 3, E12, E13, E23, and E123. And now we focus on this row, E1, geometry E1 is 1, E1, E2, E12, and E1, E3 is E13, and E1, E2, E1 to E1, E2 is just E2 that we have, we know that E1, E2 is equal to E2, because this will just become 1 due to the scalar square property. So this, the same reason, they will be E3, and this will be E2, or E123, which is a trivector. And now comes the case E1, E1, E2, E3. it will just E1, E1, E2, E3. This 2 is equal to 1, so it will just become E2, E3, which we will write in shorter called E23. So this will become E23, which is here, this guy. And then now we work on E2. So E2, E1 will be minus E12, and E2, E2 is 1. E2, E3 will be minus, no, sorry. Oh, yeah, wait. Okay, it will be E23, E23, and E2, E12 will be minus E1. It's because E2, E12 is equal to E2, E1, E2, and swap the order between these two, you get E1, no, sorry, E2, E2, E1, and you get minus E1. So this is why the E2, E12 is equal to minus E1. And now E2, E13, oh. So E2, E1, E3 is equal to, this is just a trivector, but since we want to express into the same basis, so we would like to swap the order. So we just swap the order between these two. So it will be minus E1, E2, E3, it will be minus E1, 2, 3. So it will be minus E1, 2, 3. And E2, E2, 3 will be E3. And E2, E1, 2. So E2, E1, 2, 3. So E1, E2, E3. In this case, we would like to swap the order between these two. So you get E1, E2, E2, E3. And these two are equal to 1. So we get E1, E3. So it's equal to E13. And we have basically the same story for E3 when in this row E3. So E3, E1 be minus E13, E3, E2 be minus E23, E23, and and the E3, E3 is 1, and the E3, E1, 2. This one E3, sorry, try to remove all this. E3, E1, and E2. So we need to swap the order between these two. So E1, it will become E1, E3, E2, and then E1, E3, E2, and swap the order between these two again. Then it will be this minus here. There's a minus here. And then swap again, the minus sign, minus is plus, so it's gone, E2, 3. So yeah, this is actually E1, 2, 3. And E3. So it will be minus E1. And E3, E2, 3. e3, e2, 3 will be minus e2. And then e3, e1, 2, 3. It will be swap the index twice, so you get e1, e3, e2, e3, and then minus, and then you swap them one more time, e1, e2, e3, e3, which they're gone, which go into e1, 2. Yep, I forgot the arrow there, but I think it's fine. You get the idea. Now it's the bivector, dual vector, e1, 2. Oh, e1 to e1, so we will minus e2. And then e1 to e2 will be e1. And then e1 to e3, e1 to 3, and then e1 to is minus 1. And then e1 to e1 3. Well, e1 1, e1, e2, e1, e3. Then you swap the order between these two. Then minus e1, e1, e2, e3. It will become minus e2, 3. So it's minus e2, 3. And e1, 2, e2, 3. e1, 2, e2, 3. So just e1, e3. And then e1, and then e1, 2, e1, 2, 3, e1, 2, 3, e1, 2, 3 is equal to is equal to minus e1, e1, 2, and e2, 1, 3, and then it's equal to this e1, e2, e2, e1, e3, and these two guys are gone because they are 1, so it's minus e3. It will be minus e3. And then we have e1, 3. e1 will be minus e3. Yep. And then we have e1, 3, e2. It will be just calculated. No, sorry, e1, 3, e1, 3, e2. Just swap order, minus e1, 2, 3. Yeah. Be minus e1, 2, 3. And e1, 3, e3 with just e1, e1, 3, e1, 2. So it just e1, 3, e1, 2 is equal to just if we swap them, it will be minus 3, 1, e2 be minus e2, e3, 2 will be e2, 3, e2, 3, and e1, 3, e1, 3 is just minus 1. And then and then we don't calculate these two first. We calculate this four row first. E23, E1. So this means that E23, E1 is equal to, we need to swap the order, minus E213 and plus again E1123. So E123, and then this E23, E2 is E3 minus E3, and then this gets E2 and E23, E12. So let me try E23, E12 equal to, I swap them both, so minus E32 minus E21 is minus is plus, then we have E31, which minus E13 minus E13. And perhaps you can see that we still have some of them need to calculate, but you can kind of see the problem. You see that this diagonal, and if a scalar to vector is a symmetric, E1, E1, E2, E2, E3, E3, and for the vector to bivector, for the vector to vector is anti-symmetric. So this is E12, this is minus E12, and this is E13, this is minus E13, and this is E23, this is minus E23. Yeah, and the relation will be either symmetric or anti-symmetric. So, but let us carry on the calculation. So we have E13. Now we go back here to calculate this one. E13, E23. So we have basic swap. So it will be this is E13, E12 minus, I think minus E12, because we swap the order of these two, so we get the minus sign. And then yes, that's correct. So E13, E1. So when we have E13, E2, E123, 123. We first swapped E13, 123. No, sorry, E31. Then have minus E3, E23. Then we change these two, swap the index again, we get the minus sign. And then what we left is then we have a 3 here, then we have a dot product with the E3, which MTL, and then flip the sign, so will be E2. Then E23, E12, no, here is E23, E13. Then let's calculate this. E23, 13 is minus E23 E31, so it's minus E21, so it's basically E12 E12. So E23 is minus 1, we know that. And then E23, so it's E23, E23, E123, it will be, I need to swap. So let this for sure be E23, and swap is that 213, then 23, then swap there again, so it will be 231, and then swap them one more time, 23 E321, and then is equal to E1, so this is equal to E1. Then E123 E1, so let us calculate E1 E123 E1, then we basically swap the index twice, we get E23, because we get E213 E1 minus sign, and then swap them one more time, 231 E1, then we get plus, then we get E23 E23, and we have now we have E1 E123 E2. Basically we just swapped it once, E32 E2 minus E13 is minus E13. And I did some check of the table. Turns out there's something I did wrong. First is this one, and the second is this one. So let us recalculate this. So it will be, let's calculate this one. It will be E2 E123. This we swap index, will be minus E13. So it should be minus E13, and this one is E23 E123, and it will be equal to so we do swap these two, E12 E32, and also minus E21 3, so we get E3 E13, then we have minus E3 E31, then we have minus E1, so it should be minus E1. Now we carry on the calculation, the rest of the calculation. So E123 E3, so it just become E12, and E123 E2, 1 2 3 E2, We swap this twice, so no, we it will be minus E13, E12, and it will be minus, it will be plus again, 2, 3, 1, E12, it will become E3, E2, it will be minus E3, E2, E2, that will be minus E3, it will be minus E3. And the rest of the calculation, we will still carry on. E1, E1, 2, 3. Now we have, wait a minute, arrow. Sometimes I forget the arrow. Oh, I forget quite a lot the arrow, but I think you get the idea. Yeah. That is E3. Yeah. And now it's E1, 2, 3, E1, 3. And then we swapped E2, 1, 3, E3. So instead of swapping them, we already know what happened to E3. E3 is minus 1 from the table. E13 is minus 1, so it would just be E2. E2, and basically the same thing. E12, E1, 2, 3. Now we have 2, 3. So we have E1, E2, 3, E2, 3. We get from E2, 3, E2, 3, which is minus 1. Then we get E minus 1. So the only thing left is E1, 2, 3, E1, 2, 3. So E1, 2, 3, E1, 2, 3. Then we have okay, we swap the order, E2, 1, 3, E1, 2, 3, minus, and then we swap the order again, will be E2, 3, 1, E1, 2, 3, it will be E2, 3, E2, 3, then we know E2, 3 is equal to minus 1, it will be minus 1. And now we have derived the geometric product table in 3D. In 4D, it's basically the same story. We're just using the algebraic definition of the geometric product to carry on such multiplication in the orthonormal basis vector. One thing to notice from the table is that it will be either symmetry or anti-symmetry, which basically it could be the same or just a sign different. So that is something to be something we can get from this table, the impression from this table. And see you in the next video.